uh, and that is uh, so that is about time shared architecture and where we need to look into pipelining and retiming. So this is what we did last time before the midterm exam, that we studied time shared architecture, then how you do a state machine based design, and also we learned about fixed and floating point representation. Today we will continue learning about time shared architecture, but we shall focus on pipelining and retiming. And then I have requested Dr. Hamoud. He has access to the FPGA tools. So we have developed a few examples, and that should able to just make you understand the importance of pipelining and retiming. Uh, and that is, another very important aspect. That end of the day, whatever you develop in Verilog has to be implemented in hardware, may it be an ASIC, uh, but it has to be mapped on some technology, and technology is based on gates and transistors, and every transistor has some delay once it switches from 0 to 1. So every logic that you build has now cascaded number of transistors. These transitions, which are you are adding number or subtracting number or shifting number, so they are making these transistors to switch from 1 to 0, 0 to 1, and that switching with delays and going through number cascade of these transistors would cause a signal to get stable, but it will take some time for the signal to go from point A to point B before it is latched into another register. So that's why the we have been like stressing that once we talk about digital design at high level of abstraction, the only thing we need to know is that where your registers are. So this is very, very important for us to understand that register transfer level means that you got to be aware of all the register in your design, and in between logic which comes in the within the two register is the combinational logic, and this combinational logic is just based on the actual transistors, means gates are built of transistor. So a signal is going to take some time reaching from going through this cloud, because every transistor is just going to delay. So today we will understand that whenever you are tasked to develop a digital design, you are given a timing constraint. You are tasked to synthesize the design at a certain clock. Okay, and people want to run their circuits at higher and higher and higher clocks. So you say, let's say 500 megahertz clock. So means now you need to make sure that none of your cloud is taking more time than whatever 1 over 500 uh, megahertz is. And so in terms of in seconds, so you can always calculate the time, because once the next passage of clock comes, you must have a stable signal here, and usually there are going to be many paths. So the longest path will matter the most. So the longest path, because once the longer path gets stable, only then you should launch. And now there are all these very sophisticated and expensive tools which will show you that whatever you have designed will meet timing. That's why tools become very important, because they would just give you this comfort that yes, just don't worry about it, because I'm telling you that your design will work at this clock, so it will work at that clock. So timing closure is very important aspect of digital system design. But please also remember that while you are designing and you know where your registers are, only then you will able to do a design which definitely will meet timing. Otherwise, you do a complete design and then you find out that you have bigger combinational cloud and you have to come back to fix that problem. It becomes a very challenging problem to fix, like reducing, making a time closure by changing the architecture is a very complex problem, because your design is complete, and just breaking a combinational cloud would just change the synchronization of the circuit. So So, and we are more concerned of the data path because it is usually the data path that is doing the computation. It is adding, multiplying, comparing. So a lot of computations are happening in the data path. And usually control is just we are transitioning the states. So it has only if this is the input, so I need to go on into this state. If this is the input, I'm going to go to this state. So the control unit usually is not really very sensitive to the timing because of the obvious reasons that it is just checking conditions and transitioning to new states. So I would go back to the problem that we uh, solved, which was a comparator, a sorting architecture that you put all the inputs and in one cycle, like from one this register to this register. So we don't have any register in between, and we said just this whole combinational cloud, which is consisting of many comparators, and for the four input, you can count the number of comparators: one, two, three, four, five. So five comparators. So, and you can actually come up with a formula. It's always going to be like this. If it is five, so it is four, three, two, one. If it's six, so you can have its complexity in that how the number of uh, inputs that you have, and you want to sort them out. So, how many comparators are going to be there, and also you will also able to figure out that what is the critical path. So this comparator number two, comparator number three, comparator number four, comparator number five, this is the longest path. It got to get stable before the next pause edge of clock happens. Otherwise, you will get erroneous results. So this is very quick path. As you can see, it has only one comparator. So this register, you are not really worrying about this register because it has, and maybe you need to worry about because it is this and this, and so this. So every comparator. Uh, so there are three comparators where this signal will get stable. But in this path, there are five comparators. So sometimes, because while you are designing, you know that you are creating a very big combinational cloud, and it is never going to meet timing. So you have to think at that point, once you are designing the architecture, that should you go for such an architecture where there is a big combinational cloud, and if you really don't know where your registers are in the design, then it becomes a challenging problem to do the timing closure and just looking into the Verilog code and figuring out that where to insert registers, how to pipeline becomes very challenging. So we have learned about that you need to uh, divide and conquer. So you got to divide your problem into modules, smaller module functions and tasks, and then you need to build on to your complex designs. So from that perspective, perhaps digital system design is a good candidate for a generative tool to assist you in the design if you're a good architect. So I hope that you will keep checking. Yeah, they're still connected. Okay. So, and remember, I also showed you from the time shared perspective that what if you are sensitive to the combinational cloud and you have a lot of time at your disposal uh, to do the sorting, for example. So there, let's say in data path, you only put one comparator and you say, I will use this comparator 7 times to sort uh, these four numbers or n times to sort these numbers. So now you have to come up with a state machine which would do that. And state machine, remember last time we discussed that you are asked to do the comparisons. So you got to load one value, so read a value B, uh, then you do the comparison. So here is your cloud, which is doing the comparison. Then you need to write, and so you need to write A and write B. So that's how it's going to. Uh, so this is basically just you compare, and then you write A, then you write B, and then you go back to read A, read B. So in this, you keep on doing this till the time you are end up with all the comparators, and then you send done signal. So this is how a typical architecture works, and we worked on the data path. Now today, what I have requested Dr. Hamood to show you that how the cloud grows. For example, we took a very simple example where there are two inputs. So this is a module. We said, okay, design a module where you get two inputs. So this is input one, this is input two. And because once you are doing timing, it is a register to register. So we have a register right at the input of these uh, module. As soon as the signal gets in as a positive edge of a clock, you store this value in this register and the input 2 into the other register. And here is your combinational logic, so to say. So this is where you are doing the comparison, and here we are finding the maximum. Just to make it a simple example to understand the synthesis, so we are going to just find the maximum of the two values. Okay, so we said let's just find out the maximum, and output is the maximum of these two numbers. So as you can see in this module, you have obviously a clock and a reset and an input coming in and input 2 coming in, and then max out you are sending. So it is going to take a number of clock cycles because you get this on only on the positive edge of a clock. These gets here and you get an output. Then the next positive edge of a clock, okay, this is where you put them here. So once you send some value here, it is going to take two clock cycles. To one in one clock cycle, the value will come here, and in the next clock cycle, the value will get out to the output. So it is because of the reason that you have inserted two registers into the data path. So this is simple logic. If you assert reset, it's the pause edge clock or pause edge reset or neg edge reset. So you latch these into register 1 and register 2, and then you compare what is the maximum value. So if register 1 is greater than register 2, register 1 is maximum, otherwise register 2 is maximum. And then whatever is the value, you latch it into another register, which is a max out register. So this max out will then is this register and value will go there. So today we are going to synthesize this on an FPGA for you to find out that how much is this delay. Okay, and this delay will dictate that how fast you can clock this simple circuit, which is finding the maximum of the two values. Now what happens is I said now start increasing the size of the combinational cloud for you to see that once you increase the size of the cloud, obviously the critical path will increase and you will not able to uh, latch the or clock the circuit at a faster clock. So you got to compromise on the speed of the clock, or you need to do something other than that, and that is what we are going to learn today. That you got to pipeline the design. So these are the three values. These are three registers. This is the maximum value. Same thing that at the pause edge of a clock, you latch the input in 1, in 2, in 3, and now you are doing two comparison. If register 1 is greater than equal to register 2, and register 1 is greater than equal, so still it is trying to do a lot of things in parallel, but still it does this if first, and then it does else if, and then it does else if, and figure out. So there are going to be uh, and because we are designing at a high level of abstraction, so we are not really worried about to understand that how this logic is going to be constructed. All we care is that there is some logic which is a combination logic, and because now we are doing finding the maximum of three numbers and trying to do this in a single cycle, so obviously the logic is going to grow. And so there are three registers here which we are going to see once we synthesize the design. You will able to see the register, and Dr. Hamood may able to just show you the schematic as well for you to comprehend that yeah, these are the three registers. And now we will see that how fast will you be able to clock this circuit, and then once you get the value, you put it in this output register. Then I said, what if you have four input? So these are the four input in 1, in 2, into 3. And now you see that now they are like, though you are doing a lot of parallel comparison, but you first decide whether register 1 is maximum of all the other values. If not, then you check with register 2. If not, then you check register 3. And finally, it is register 4. So it's again, you are increasing the size of the cloud, the cloud, and putting more and more and more logic into the finding the maximum in a single cycle, right? And then same code is repeated here. Then I said do it with 10 values. That if you have 10 inputs and you have these are the 10 inputs and you were to find the maximum. So it's like as in a two set of codes. One is this, the other one is consistent with what it has been producing. That first it checks with whether register 1 is greater than all the values, or if input 2 is greater than all the values, if it's 3 is. So it is just checking all these, and obviously it has not to check the 1 and 2, because if register 1 is not greater than 2, only then it will come and execute the statement. So you will find register 1 is not here, then register 2 is not here. So the size of it is reducing, but a big cloud here. So you have increased the size of the cloud, because now you are finding out of 10 numbers which one is the maximum number. And so today, again, as I mentioned earlier, we are going to see that what if we have all these comparators, and how many comparators are going to be there. There are many, like you can perhaps count, and it may the synthesis rule may able to optimize the combinational logic. So definitely, you'll do a try to optimize the logic. And as I earlier mentioned, you really don't care that how this gets inferred or implemented. Okay, you all you know is that this is a cloud which is going to give me an output value, and but you are making this cloud a very big, going to have a lot of delays. So one thing to handle such a situation is that you pipeline your design. So pipeline is almost similar to if you see a baker's or a tandoor wala, making rotis. So you will find like 2 3 people doing this job, and that is the principle of pipelining. That one is only just वो पेड़े बना रहा है, दूसरा उसको तंदूर में लगा रहा है, तीसरा जो है वो तंदूर से निकाल रहा है, चौथा जो है उसको अखबार में लगा रहा है और उसको कस्टमर को दे रहा है. एंड देन अगर इट इज अ सिंगल पर्सन हु हैज टू first वो पेड़ा बनाए, then put it in the tandoor and then wait for it to be cooked, then take out उसको अखबार में डाले and then give it to the customer and then comes back, is going to take him a lot of time. So by pipelining, a very simple principle of pipelining, you can increase, though it will still take the same amount of time for chapati to be cooked and got into a customer, but the throughput will increase, because the throughput will depend upon the slowest stage in the pipelining, and that's how you try to make sure that every stage in this pipelining is balanced, is almost the same. And that is the challenge of pipelining, that how you pipeline your design. For example, it's the same case where if this guy who is making a peda takes 5 minutes, but this guy who's putting it in the tandoor only takes 1 minute, and it gets cooked in 1 minute, and he's fine 1 minute. But this will determine that how fast you can cook the chapatis, and because the slowest stage in. So another challenge of the pipelining is that every stage of the pipelining has to be equal. So pipelining is so can be easily understood that pipelining is where you have a big cloud, and you have this thing in mind that you want to clock this circuit at a very high clock rate. So you cannot have a very big combinational cloud between two registers. And once you know that you are not going to have a big cloud, so while you are designing, you will devise an architecture where you would break it down into multiple parts. Okay, and you will insert register in between. It will add latency, means sometimes we are not very sensitive to latencies. The reason is in real-time application, let's say voice that you're talking to someone, or the Zoom call, for example, that I'm just talking and you are listening, and this Zoom call is going through a lot of logic. It is getting, my voice is getting compressed, my video is getting compressed, and there's a network, there are routers and switches, and taking it from Kuala Lumpur to Pakistan. But because of the speed of the clock is such, if it is 1 gigahertz, so one clock cycle is 1 into 10 raised to the power minus 9 seconds. So you don't care in real life. And so usually by inserting registers would cause definitely a delay from an input to appear at the output. But in real-time application, because of the speed of the clock, that delay is not that much. So you usually are not concerned about uh, this, but definitely once you are inserting registers and you're clocking a circuit at a faster clock, it is going to dissipate more power. So it will become power hungry because of the switching of the registers and because of the clock. It dissipates more power, but sometimes power is not your concern, speed is your concern. And we are also going to learn something very interesting, which is called retiming. Retiming is that if you have a cloud, okay, and you have some registers somewhere which are not really helping you to breaking any combinational path. So there are like three or two registers cascaded because of these are the algorithmic registers. They are in cascade, and they are not really helping you uh, to break this cloud. So you will move. Sometimes the synthesis tool would automatically move if you enable retiming. Synthesis tool will systematically will move the registers, the algorithmic register of your design into larger combinational cloud, breaking them into pieces. So it would just move all these three registers systematically in such a way that this bigger cloud is broken down into three parts, and so that you can, without inserting pipelining register, you retime and you do. And another way of thinking about retiming is that you add pipelining register at the input and then systematically move them inside and place them where you can actually break the combinational cloud into pieces. So this is a very interesting way of looking at the pipelining. So pipelining usually is for circuits which are feed forward circuit where nothing is fed back into the design. Okay, for feedback circuit, adding a register inside the combinational cloud will change the difference equation, will change the order of the difference equation, because usually once you have a feedback system, it is implementing a differential, or if it is a discrete system, it is implementing a, a feedback loop. And feedback loop means that you are feeding the output back, and if it is going through one register, so in your algorithm you are using the just the previous value of the output, so y of n minus 1. So this is the previous value. Inserting a register in between would change the equation, and which will just change the logic, and which will change everything. So we are very cautious once we have the feedback systems. The feedback systems are very challenging to design and to be pipelined, right? But feed forward systems, they you can just add as many registers as you may want to. All you have to do is that you need to figure out all the paths which is going from input to output. So this is important, and this is the cost of pipelining. That do you want to break a combinational cloud, and I'll show you an example. Let's say here is a combinational cloud, and but then there are other parallel paths which has smaller clouds, and there are many of these which are even smaller cloud, and but somehow they all are coming in here, and uh, and so all the outputs of the clouds are coming in here and then going through some other computation and then generating an output. Now, though this is the path which is not meeting timing, and you want to break it down. You cannot just put a register here. So you have to put a register in all the parallel paths. So finding out all the parallel paths in a digital system, and if they are going across the module becomes very difficult. So that is the reason we always try that a module should be uh, partitioned, the design should be partitioned in a way that all your inputs and outputs shall be registered, and that will give you a comfort that by putting a pipelining, you only have to focus on one module. But if module boundary is something like this, that this is part of your one module, and this is part of another module, and this is part of another module, and then pipelining this design or this implementation will be very difficult. Figuring out that where are you all your parallel paths, and because you cannot just everything has to be delayed by one cycle to be consistent, to be synchronized. So this is one of the challenges of pipelining, that you got to be synchronized. Otherwise, it is like if two people are going through different gates and they are meeting and going forward, and one is delayed and one is fast, so obviously you are going to change the order in which they have to go and get out of the system. So everyone has to be delayed by the same amount of cycles. So all the paths going from input to output. So that's why this pipelining, the theory of cut set is important. That once you are designing, just design your logic and then put a cut set. As I was doing it here, the I told you that okay, I count there are like longest path is 1, 2, 3, 4, 5. So I said put a cut set here at that time, and I said we'll study that what is meant for this by this cut set. Means okay, I'm going to put a register here. Sometimes it is not convenient to put a register in something which is actually computing. So then you can compromise that I'll have a little imbalance partitioning. So this part will have three comparator, this part will have two comparator, but have very neat and clean pipelining. Getting inside a computational block and pipelining it sometimes becomes challenging. So we try to avoid it, and we do some compromise that let's not exactly partition the design into two parts. So this is the way. Like now, let me show you an interesting circuit. So these are algorithmic register. Okay, so you don't need to understand what the circuit is actually here, except that it's very obvious that there is some input coming in and it is stored in a register. Then there is a previous value of the input. Then there is, so these are all algorithmic. So it's kind of the weighted average where you have the previous to previous value and previous to previous to previous value. And so you are assigning every value of weight h0, h1, h2, h3, h4. So you are doing this multiplication, then you are adding to get an output. So it's simply a weighted average that you are transforming an input using its previous values. Usually it's like we call this smoothing, but depending upon the coefficients, it may have like different meanings. But important is that the critical path. So critical path is the longest combinational path. So there is a multiplier, there is an adder, then it has to add this, then it has to add this, then it has to add this. So all the multiplications are happening in parallel. So I may be concerned about all this multiplication happening in parallel is causing me some area, but then I say I am okay if I am spending area, because my first desire usually area is we have little concern of area because of all the refinement in the technologies where there are like billions and trillions now are gates available to you on a silicon or even on FPGAs. So the more concern is about the speed at which you can clock your circuit. So now you're finding out that so many adders, and adder is pretty combinationally complex device. It takes a lot of time for a signal to settle down once it go past an adder, and multiplier is even more time consuming, so to say. So this is a critical path. And if you know this circuit, I cannot, by looking at it, I know that I will not able to clock it at a desired clock, which is given to me as a target clock. So the simple way is that you put a cut line and you put registers. So you say, okay, this is I cut it into half. So one is multiply two adder or two adders here. Or you can, if you want to, you can even put a cut line here where you have multiplier and adder and then three adder. So you have to decide that which would best partition your cloud into two parts from the time perspective. So let's say you have decided to put your cut line here. So all the paths from input to output must see same number of registers. So they are all on here in this cut set line. There are only two paths. One path is this, the other path is this, and so you're putting a pipeline register here and here. But interestingly, if you look at this register is not really helping you uh, to partition your cloud. This register is not helping you to partition your cloud. This register, all these registers are cascaded, and they are not helping you to break down your combinational cloud. So if somehow you can move these registers into places in your design, in your algorithm, which would help automatically. And because putting an extra register is going to add delay, you are going to add more latency, and this extra hardware. Whereas these all these people, these are kind of employees which do nothing, right? And except like delaying, just doing some uh, storing something. So just storing, let's say you're moving a file and it's just file keeper, but actually these are the people who are doing things, and you got to somehow facilitate them by making them do some work, and where there's some work, and then the file should go and stay with with the storage elements. So uh, this is where we need to learn about the cut set retiming, that you retime a circuit. So, and this is even if you have feedback. So as you can see, this is a feedback system, and dot mean a register. So here is a path which is going this way, and here is a path which is going this way, and here is a path which is going this way. Okay. So in cut set retiming, you put a cut, and you can move equal number of registers going in one direction and move them to the other direction. Equal number of registers. So, for example, this path moving in this direction, this path moving in this direction, this path moving in this direction. So I can take this register, and this will also help you to reduce the number of registers and make them do some useful work. So these two registers you remove and bring it here. So as you can see here now, so there is a register here, there is a register here, and so you have broken down the combinational cloud. But this example is just to demonstrate that cut set retiming is a technique where registers can move inside your algorithm from paths moving in one direction to path moving in another direction. Provided that you have on every path that is moving in one direction, you have the number of registers which can be moved to path moving in the other direction, and still you are algorithmically consistent. So, uh, and here is an interesting example. You see this path moving in this direction, this path moving in this direction. So this path is moving in this direction, and this path is moving in this direction. This path is moving in this direction. This path is moving in this direction, and here is your output, and this is your input. Okay, so you have drawn this a feed forward circuit, but you have drawn it in a manner that now you see two set of paths. Now, interestingly, you can move this register from this path to this path. You can move this register from this path to this path. You can move this register from this path to this path. And now a circuit which looks like this, having all these registers, not helping you to break the combinational cloud, is now look like this, where all these multipliers are parallel. So you have an input that goes to all the multipliers, and then you have a register, and now you have delays, and your now critical path is a multiplier and an adder, and then there is a register multiplier and adder, then there is a register multiplier, there is a register and multiplier and adder. So you have reduced your critical path from one multiplier and three adders to one multiplier and one adder by not inserting any pipeline register, rather moving registers systematically. And as I mentioned earlier, that sometimes if you let the synthesis tool do this for you, it will also I am not sure if we could able to demonstrate it to you today or not, but we definitely would show you that if you enable the retiming, it will do the retiming for you. But then uh, the the synthesized code would have a bit different architecture, where the registers where you place them in your Verilog code would appear somewhere else in the synthesized code. But sometimes you really don't care. So this is the reason, because of the task. For example, in every processor, like a Pentium processor, okay, all you have to do is that you have a processor, you take an instruction in the program memory. So this is the instruction in the program memory, and if this instruction wants to do something, maybe it wants to multiply two numbers and store the value back in the memory. So there is a task which this instruction needs to do, and this task can be done. That first you need to figure out what first you need to get this instruction from the memory, then you need to decode it, figure out what this instruction wants to do. Does it want to multiply numbers, and which number, where those numbers are? Okay, so operands are fetched, then actual operation, then does it want to store something somewhere, and then storing. So though all these things can happen in a single cycle, but then you will not able to clock your Pentium processor or Intel could able to clock its laptop computers at 1 gigahertz, 2 gigahertz, 3 gigahertz. It is only because they pipeline it. They say even fetch is 2 cycle, decode is like 3 cycle, and the rename, I think read operand, so dispatch, execute. So, and as they are moving from Pentium 3 to Pentium 4, they are increasing the pipelining from uh, a 10-stage pipeline processor to a 20-stage pipeline processor. And that's how they could actually clock it at a faster and faster and faster rate by the principle of, at the design time, breaking a task which could otherwise can happen in a single cycle, making it happen in 20 cycles. So once you pipeline something, the pipeline hazards, and those of you who would select the architecture uh, line of our course would learn about what are the pipelining hazards, how you deal with those hazards. So those who are more interested into the architectural design, uh, then you can get into uh, uh, that what happens if there is a branch and there are like 20 means at every clock cycle there are 20 instructions in the pipeline. Okay, so the instruction which came 20 cycle back actually gets completed. Right, so this is same case in industry. और जो मैं आपको तंदूर की एग्जांपल दी है, like if the tandoor is burning all the rotis and you will only figure out once a roti comes out, and but you realize that there are 20 inside this because of the pipelining delays, and so you have to if for example you find out this actually wanted to branch, and all the instructions, it just keeps on fetching instructions sequentially, and this instruction was a jump instruction, and it is after many cycles you find out that you are not really executing a, a sequential code. You have to jump somewhere else and fetch another instruction. So all the instructions which are in the pipeline are to be flushed out, and then you have to refill the pipeline stages. So pipeline penalties are much more, and then people are trying to address this by predicting that if there is an if, so 90% of the time if is actually true. That's how people code it. and it is very rare that if would go false. So they say let's keep on assuming that if is true, execute, and but only if you find out, oh no, my prediction was wrong, and then you have to go and flush pipeline. So a lot of sophistication in dealing with pipeline hazards, and I know for sure people doing their PhDs in just dealing with the pipeline hazards. So pipeline hazards are something that you got to deal with them, especially if your logic is very complex, and especially if you have an instruction set processor, and then you got to worry about how are you going to flush uh, the things which are their pipeline, and because now you figured out that you got to do something else, not so there's people coming in and say no 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 I have to do something else because of this input. So another way of moving registers in your design is that it is called node transfer theorem, that you can move number of registers from a node going out to a node coming in, from input to output and output to input. Now, obviously, I cannot move this register across this node because I don't see any register on this branch. Okay, but on the other hand, I see a register here, a register here, a register here. So there are three registers. If I move these three across this node, then I'll be able to reduce the number of registers and maybe make better use of them. This is also kind of retiming, but using a node transfer theorem. So you remove these three registers from the outgoing branches to the incoming branches, and you are left with only two registers. So this is called node transfer theorem. So here is an example of the node transfer theorem where you have two registers. So you take these two registers and move them to the input, and now you have only one register. So you are saving, and the converse is also true. Okay, so sometimes you and we'll see an example. You put a pipeline and then you um, uh, uh, apply the node transfer theorem and make just one register which you have added at the input. That register going to all the branches and helping you uh, to break the combinational cloud into pieces. Here is another example. It is just a ripple carry adder that you add 2 bits, carry goes here, sum goes here, and then based on this carry, you have these two inputs. Then the sum goes here, carry goes here. Then you again have this carry out and these two inputs, and because now this is a combinational cloud, this is your critical path. The critical path is your carry going through, rippling through all the full adders to get to the final carry out. And this is the slowest adder in the adder family. And because the carry has to go pass through all the adders, and that's how we also add numbers. That once you are adding numbers, we know from our class class one or maybe class two that the carry has to be propagated forward. So you say 1, 1 plus 1 is 0, so carry is 1, 1 plus 1 is 0, carry is 1, 1 plus 1 is 1, and 1. So it is the carry in hardware uh, going through all the full adders. If it's a 32-bit adder, so it becomes very slow. And so you say, okay, either I use a fast adder, which we studied earlier, or you say I will put a cut set. But cut set, remember, it has to cut all the paths moving from input to output to make sure that it remains synchronous. So in just one adder, that one register that you want to put here to delay this carry, to cut this full adder into two parts, you have to delay the inputs. Otherwise, these adders will add wrong inputs. Everything has to be delayed. Okay, and similarly, you have to delay these outputs. So every path going from input to output must see the same number of registers. So there is one register that is for every, so this is the design. Now you see this path sees one register, these paths sees one register, these paths sees one register, these paths sees one register, and these paths sees one register. So that's something where we got to make sure that every path going from input to output must see the same number of registers, and that you ended up just though you wanted only to have one register here to break the cloud into two full adders on this side, two full adders on the other side, but you end up putting so many. And if you want to even further clock it at a faster rate, and you have decided that you want to clock it to the delay of a full adder, so you have to cut it here, cut it here, cut it here. But then you end up putting a lot many registers because every path has to see the same number of registers, and so these are the three registers. Every path see three registers, three registers, three registers, three registers, three registers. So though you only wanted to have these three registers, but you end up putting a lot more than just the three. Rather, you have like 12 extra registers. Uh, I should not say extra. Synchronization registers, which ensure that your inputs and outputs are consistent, right? So sometimes it is better to draw it like this so that you see ladders are drawn like this so that you are putting a cut line here, cut line here. So cut lines are to draw your digital circuit in a way that your cut lines are just straight. So that's also one way of. So it is same as this, but just drawn differently. So another way of pipelining is that the nodal transfer theorem. You say these are all my inputs. These are the bits that I am putting in and I carry in. I put a register here. And then now, as we have learned that these three registers, so this is basically a register on every bit or every wire, and you can move these three registers from here to here. Okay, so there will be no register here, no register here. What you can do is you can have so that's how then you can have a register here, a register here, a register here. You can move this register here. So that's how you can place a register. So sorry, it has to become here as well. So through a nodal transfer where you have a node and you take equal number of registers from all input to move them to all outputs, applying the nodal transfer theorem. So here is so this is though I already explained that how this is Intel's atom architecture, which is a 16 line stages. So there is instruction fetch in 3 cycles, instruction decode in 3 cycles, instruction dispatch in 2 cycles, source operand read in 1 cycle, uh, data cache access if it needs to will take 3 cycles, execute in 1 cycle, execution and empty handling is another 2 cycles, a commit maybe writing it back to another cycle. So that's something where pipelining has fairly deep. So it is a 16 stages, and there is a 13 stage misprediction penalty. Like if you usually the code you keep on fetching instruction, 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 and it is saying that after 13 stages you will figure out that actually you have made a mistake. Okay, in this once you execute, you figure out, oh, I have to go somewhere else. So something like this. So you have to flush the pipelining because of this that this is where you find out, and now all this are invalid instructions are to be thrown out of the pipelining. So again, as I mentioned, that those of you who would get into more interested in architecture would study more of this of pipelining hazards. So I'll just skip all these from here. So a lot of stuff which that you are going to study, but I'll come back to this. That node transfer theorem. I have moved these three registers from these paths to these paths. Okay, to, from three input to two output, and I have just shown this here. Now I move these two register and this register to these two paths in the next here. So this is a good design. where two full adders, I have systematically able to move a register to break my critical path into two parts. And these are there for the synchronization, that all these inputs are to be delayed, all these output are to be delayed. So this full adder will have one cycle delay. Once you say add this, you will only see the result in the next clock cycle, because of this every path is seeing one clock cycle delay going from input to output, and you will get a fully synchronized output. Okay? But you say, no, I want to have like everywhere I want to put a registers. I want to really clock it at a very, very fast clock. So you say, let me just put three registers and move them to this place and this place and this place. And so obviously now you have these three registers and these three registers. Okay, so you move them here. All three will come here. All three will come here. Okay, so this is. Now what you do is you take two of them from here, two of them from here, and move them across this register, this full ladder. So now it is like this. So now what you do is you just leave one register here. Okay, you take this one and move it across this and this. So you will have this design. And now this has systematically, what you have done is that the amount of pipeline registers that you want to take into your cloud, you insert them at the input, and then systematically you keep leaving a register where it has to be left. Moving forward, another lever register, another lever register, and if you do this systematically, so your the entire design would basically be able to run at a very, very fast clock rate and will be synchronized. So you don't really have to worry that these are my paths and how I'm going to figure out if I want to deeply pipeline a design. Uh, so, uh, so it becomes important that you could able to draw a design at a level of abstraction where the clouds which you want to break down into pieces are separately shown in your diagram. So cloud, this example is where we just adding two bits together, but this may be a bigger logic. But important is you should able to draw at a high level of abstraction. You should able to draw the computations that you are doing into smaller cloud, and then should able to draw it in a manner where you see all your inputs and where you see all your outputs, and now systematically get into the cloud, which is shown broken down into pieces, and keep leaving registers. And now this is a good DP pipeline design where, because you were given a target to run the circuit at a very, very high clock rate, and you can actually achieve this. Okay, so you could able to achieve this. So here is the design. So, so this we have already seen. I'll not get into the DFTs. Now comes the challenge. Challenge is, what if you have a feedback? Okay, definitely feedback. You can have retiming, that you take a register from an input from this and move it here. Uh, yes, you can uh, uh, move this register uh, which is in one direction to other direction, or what you can do is that you open up this equation and algorithmically add register. How you can do this? By writing this equation for y of n minus 1. Okay, this is a trick. Actually, I could able to supervise a PhD thesis by applying this technique to some FIR, IAR filters designing, hardware designing, that how you can make an IR filter run faster. So, so this design is where you are always using the previous value. So if you are computing yn as n minus 1, so you are computing y using yn minus 2 plus previous value of n, x of n minus 1. Now what you do is you put this value of x of n minus 1 in here. Okay, if you do that, now your y of n will have two registers in this equation, because now it depends upon y of, so once you put this here, so a gets multiplied with a, you get a square, and you get y of n minus 2 plus a x of, so you're not really concerned about the feed forward part of this equation, because that does not really hurt. You can always uh, delay this, but n plus x of n. This is very neat technique, that now instead of having one register in your cloud, you have systematically you have put two registers, and two registers can help you to break your critical path into three pieces. Okay, so and if you want to make it run faster, you apply this equation another time. Now you find out y of n minus 2, put it here. This will depend upon y of n minus 3, and similarly, depending upon that, how many registers you want to put, you can do this again and again. So, so this is how you do the IIR filter. Okay, I would rather not do this. So, so this is pretty much yeah. So here is another thing. Like now, look, a bit more complex example of something. Here, all these registers are not really helping you to break this critical path. So I've shown the critical path, which is this multiplier, all these adders, and this adder. So and you say, oh wow, and similarly. This is also a kind of a critical path, this multiplier, all these adders. Okay, you say I have this path, this cut line, cut line, cut line, which will take a register from here, which is cutting this line from left to right, you can say, and move it to the line which is cutting it in the other direction. So if you apply this, you have systematically bring three registers here. So moving one register from here and another register from here, you have a register here, register here, register here, and register here. So two cut set, as you can see, this is one cut set, this is the other cut set. So cut set retiming is a very interesting technique to make your circuit run faster. And okay, make your circuit run faster. So 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 this is the feedback cut set retiming, and now you have reduced your critical path into this is one adder and one multiplier and an adder, and your registers are kind of helping you to do this cut set retiming. Okay, so same is the case. I will what to do. So it's like the theory goes on and on where there are more complex algorithms to break down a node into pieces and then adding registers. But I don't want to get into more complex part. Except here, the retiming, we have learned that retiming would take across the node, you can move these three registers across the node and these three registers across the node and these two registers across the node, or by having pipelining. So you say, I want to put one stage of pipelining. So you have this, or there are two registers here. Then you can systematically keep moving them inside your design. So you can move them here, and then you can move them here. You can move these two here and here. So by moving registers to the uh, design, or you can move them out, move them in, move them out. So it's up to you that where you find the value of the registers more. So, so this is pretty much what I wanted to cover in this part of the lecture. And the second part, I want, like, we will start in uh, about uh, in 30 minutes, and at 7:30, and where Dr. Hamoud would just take those examples which I showed you in the start and do the synthesis to show you that how you synthesize your design, how you look into the schematic, and how you try to. We will make an attempt to pipeline the design, the just finding the maximum value to see that how can we pipeline it. So it's like just from the Verilog code, it looks pretty difficult to go in the Verilog code and then try to do the pipelining. But drawing it into number of clouds and then thinking about it and then generating a code that basically you have kind of designed would be easier from my perspective. But we'll see that how should we go about doing this. So let us meet again, and then we will go because I'm here at Kuala Lumpur Airport. I also need to go get my boarding card, and but we will sync again. I'll be online with Dr. Hamoud at 7:30 or 7:40 maybe. Okay, okay, so we'll see each other again, inshallah.